Welcome students, and in this video we are going to talk about well-posedness of an ODE. So what does it mean? So first of all, we start by considering an ODE. Let's consider a system. Okay, so I'm doing it for a system, but you do realize that it can be, you can use the concept for any given ODE, right? So consider the initial value problem. Let's say initial value problem. Okay, x prime equals to f of x. Clear? And x0 equals to x0. Okay, so this is given to us, right? Now where, and let us understand the start with x0 in Rn. So essentially we are talking about a n cross n system. So basically we have a n cross n system. Okay, now the point is this. You see, let's call this a star. Now the thing is, given a system like this, what do you want to do with the system? So essentially we want to study the system, but what do we mean by studying a system? So basically what does it mean? What does it mean to study star? Okay, to study the system star, the system, above system, that is. Okay, and what it means is this. Essentially, you see, we are basically looking for three main questions. So first question, so that is called the well-posedness. So basically you want to know whether the system is well-posed or not. Okay, and what does it mean? So what are the properties which the system should satisfy for it to be well-posed? Okay, so properties. So first of all, A, the system in question star, in this question star, must have a solution. Okay, must have a solution, of course, in an appropriate sense. Okay, appropriate sense. You see, solutions can be in many sense, right? Appropriate sense. Okay, must have a solution in an appropriate sense. Okay, so first of all, it must have at least one solution. That's what I mean to say. It means at least one solution. Okay, and whatever you want to call, whatever you mean by solution, I was talking about that sort of thing. So at least one solution should be there. B, if, so first of all, let's just put it this way, that once you have found a solution, now the thing is, if there exists a solution, it should be unique. It should be unique. Clear? So basically there cannot be two solutions to star, right? So if you have a system or any equation for say, okay, and if you can find out that that system actually admits two solutions, okay, so whatever the meaning of solution is, by that meaning, if you have, let's say, two solutions, then of course it is not well posed. So basically you have to have first of all one solution, and the solution has to be unique. So those are the two properties, and the last property is called the continuous dependence on initial data. Continuous dependence on the initial data. Okay, so what it means is this. See, for now I am not going to make it much, so we will make it much precise just in a minute or so, but first, for now, let me just put it this way. What it means is, let's say if you start with x0, okay, you get a solution, right? Let's say xt you get. Now what do you think what happens if you start from, let's say, x0 plus delta x0? Okay, so let's say x at the point 0 is x0, right? And the system does something, so basically you get a xt. Now let's say if you are starting with a x0, which is x0 plus delta x0, you are probably going to get a yt, right? Because you know there is a solution and the solution is unique. Let's just remember that that is true. Once those things are true, now you see, for x0, starting from x0, you have x of t, and if you start from x0 plus delta x0, you have y of t. So what do you think is the relation between xt and yt? Okay, see, if x0 and delta, so x0 plus delta x0 is the difference. So let's say if delta x0 is sufficiently small, okay, in some sense, I am not putting it like this. So basically if it is sufficiently small, you expect your xt minus yt should also be, I mean, you can make it sufficiently small, right? So we are actually looking in that direction. So essentially, what it means is, if you change the data a little bit, you also expect your solution to change a little bit, right? Okay, all of this I will make it very precise, just in a minute or so. But you do understand what the concept of this. Okay, right? And this is very, very important property. And now, if the system, so basically, let me put it this way: if star satisfies A, B and C, we call it a well-posed system of ODE. Clear? System of ODE. Okay, right? So that's the main idea, right? Now let's say I give you a system, right? Whatever it is, x prime equals to f of x. Some system is given. You know what that vector field f is. So here f is a vector field from, let's say, Rn to Rn is a vector field given. Vector field. It is given to you. Clear? Okay. Now the point is this: I want to study whether the system is well posed or not. So what is the first thing we need to know? Whether there is a solution or not. If there is a solution, whether the solution is going to be unique or not, right? Okay. So here we already know, we have seen in the last lecture the existence and uniqueness theorem, right? Picard's existence and uniqueness theorem, which you also call the fundamental theorem, essentially uniqueness theorem. So let me again state it here, because anyways it is very, very important and we should always know this. Okay, so what we have is this: let's say if capital F from Rn to Rn, okay, the vector field in question is C1, right? Then what do you have? Then star, right? The system, you see, x prime equals to f of x, x0 equals to x naught. This system given f is C1, okay, admits an unique solution, in some neighborhood of 0. Okay, in some neighborhood, let me put it this way, neighborhood of 0. Okay, and what is this 0? This 0, this is what the 0. Okay, so essentially this is t equals to 0. Okay, so 0, clear? Okay, so in the neighborhood of 0, minus epsilon plus epsilon, you can actually choose an epsilon such that this system has a solution. Okay, that's what we have. So essentially, let's say we are assuming f is C1, which is not a very, very strong assumption. It's okay. So with that, we know that there you always have a solution which is a unique solution in some neighborhood of this thing, the origin, right? Now what? Okay. Now what about the third property? So basically, A and B is taken care of. If f is C1, we know that A and B is satisfied, right? If f is not C1, then there can be many different cases. It may not have a unique solution, or it may not have a solution also. Okay. So f is C1 is okay. That we know that A and B is satisfied. Okay. What about C? So before we go on with the C, let us just make it more mathematical. What does it mean for a continuous dependence on initial data? Okay. So what it means is this. See, what I let us write down a theorem in this thing. Theorem. This theorem will actually clarify what I mean by continuous dependence on initial data. So let omega subset of Rn. This is our assumption. I am assuming omega subset of Rn here, and f is a vector field, right, from omega to Rn. This is what we are assuming here. Omega to Rn is a vector field, okay, with a Lipschitz constant k. With the Lipschitz constant k. So basically, we have a Lipschitz continuous function with a Lipschitz constant k. Let's just put it this way, k. Clear? Okay, so k is in R. You do realize that, right? Lipschitz constant. Okay, you remember when it is Lipschitz. So f is from omega to R. Basically, it means that f of x minus f of y has to be, the norm has to be bounded by k times norm of x minus y. You remember that for all x y in omega, right? For all x y in omega. Okay, that's what Lipschitz means, right? Okay, right. So we are assuming this thing. So please remember this thing. See, The thing is, for the well-posedness we did it for a C1 map, C1 vector field. Now any C1 vector field is locally Lipschitz, right? This is locally Lipschitz, but may not be Lipschitz. It is locally Lipschitz. Okay, it is locally Lipschitz. Now here what I am saying is you need your vector field to be Lipschitz continuous, right? Now if that happens, we are assuming y of t and z of t be solutions of f prime equals to f of x, right? Okay, which remains in omega, right? Which should remain. You see, the thing is, you see both the solutions yt and zt, you are getting two solutions, right? And the thing is, those solutions has to be in omega, because otherwise f is not defined, right? So we have to have that those solutions must remain in omega, right? Because f depends, see, for every t, x of t, okay, x of t should be in omega, because you also have to define f of xt, right, for this equation to work. Clear? So this x of t has to be in omega. So basically here I am starting out with y and z, those should always be in omega, okay, and are defined, okay, on an interval, let's say some interval, right? And let's just put the interval as t0 to t1, some interval. Clear? Okay, then for all t in t0 to t1, we have, okay, now this is what we mean by continuous dependence. You see, norm of y of t, see yt and zt for given t is in Rn, okay. So yt minus zt should always be bounded by y at the point t0 minus z at the point t0, okay, times some exponential map, and which depends on k times t minus t0. Clear? Okay, so you do understand, see, if yt minus zt, right, see, t is varying between t0 and t1, right, t is varying in a bounded domain, okay. So exponential k times t minus t0, that's a bounded function essentially, okay, and k is fixed, that's the Lipschitz constant. Now you see, if your yt minus zt at the point t equals to t0 is sufficiently small, of course yt minus zt you can make it as small as you like, right? You can always find a delta. So given an itself, you can always find a delta. So that's what I mean by continuous dependence on initial data. So this is what it says, right? So again, let me put it this way in case you forget. If the solutions, it means that if the solutions, what are the solutions? Yt and zt, right? Yt and zt. Clear? If the solution yt and zt start out close together, right? So if they, if yt and zt are close together, they are very, the difference is very small, then they remain close for all time t, right? Sorry, for all time t close to near t0, right? Remain close for all time for all t near t0. Clear? Near t0. Okay. Okay. So you will have a small neighborhood of t0 where it has to be, it will be close to each other. Okay. So t0 can be 0 also, doesn't really matter, but you do realize what I'm trying to say is this, wherever you are starting out, it doesn't really matter which point you are starting out with, some t0 you are starting, and then what happens is you always have the solution actually is very close to each other, right? Okay, so to do this thing, the proof is extremely easy. What we are going to do is we are going to use the Gronwell, okay, inequality. And now what I am going to do is, since that is done in week 1, I will just quickly give the statement of Gronwell, okay. As I told you, this is very, very important, right? Gronwell inequality. Let me just write it down and then we are going to use this ground ball linear. The proof I am not doing because we already did it. Okay, so let's say that u from 0a to r be continuous and non-negative. Continuous and non-negative, right? Non-negative. Suppose c is greater than equal 0 and k is greater than equal 0, right? Are such that ut is less than equal c plus 0 to t k times us ds. Okay, for all t in 0a. What does that imply? Then that will imply that ut can be made bounded by c times exponential kt for all t in 0. Okay, so the proof, I am not doing the proof. You guys, we have already talked about the proof, so I am going to skip that part. Okay, now let's understand that what is the proof of this theorem, the continuous dependence. Let's just look at the proof of that theorem. So proof. See, the thing is, it's very simple actually, and please remember the trick. This trick we are going to use it in a lot of places. See, here I have to show that this quantity, particular quantity, is less than equal this quantity evaluated at the point t naught, see, times some exponential. Okay, so you do realize that, you see, here also I have something like this. So this constant, if I can show that this is nothing but y t naught minus z t naught. Okay, and then I am more or less done, right? Okay, and ut essentially this, if you can find this, if you can somehow write it as ut, then, and I can show that this constant will work, then we are done, right? So we have to find out something like this. Once we have something like this, that will imply this, right? You understand? So we are going to try and do that. Okay, so how to do that? Let's do it. Okay, so we will choose what? That define capital Vt. Yes, this I am defining as the norm of yt minus zt. Here, see, the thing is, t is varying between here t is varying between t naught and t1, right? So basically for that t naught and t1, Vt I will be defining to be the norm of yt minus zt. Okay, if I do that, now you see, since what is yt minus zt? You remember, you see, yt minus zt are the solutions of this problem, right? X prime equals to f of x. Okay, so those also satisfy the integral equations, right? The corresponding integral equation of what is it? So yt is given by yt naught plus t naught to t f of ys ds, and what is z naught? Zt given by zt naught minus t naught to t capital F of zs ds. You remember when we did the Picard theorem, we did the exact same thing, right? Okay, therefore what do we have? We have yt minus z of t is nothing but y of t naught minus z of t naught, okay, plus t naught to t f of ys minus f of zs ds. Okay, this is what we have. Therefore, you see, what is this? This is Vt, right? So if I take the norm on both sides, okay, so taking, let me put it this way, taking norm on both sides, what do you have? Both sides, this is nothing but v of t, and this will less, I can write it as v of t naught, triangle inequality, plus t naught to t, the norm of f of ys minus f of zs ds, right? This is what I can do. Yeah, this is triangle inequality, plain simple triangle inequality in Rn, triangle inequality. Okay, so now you see what do we have? Vt is less than equal v of t naught. You see, this is where we need the Lipschitz continuity. You see here, if I use Lipschitz continuity, I can say this is bound, this can be dominated by a constant, Lipschitz constant k t naught to t, and this y minus z, norm of y minus z, which is nothing but v of s ds, right? Now you see this is in this form. Okay, what is your constant? Constant is this. Okay, and this constant is always there, u of s ds. This is in this form, so that will imply u of t is less than equal c times kt. Here, so this will imply, therefore we can say that v of t equals to one second, I have to match this part. So one second, let me just do this part. We have to match it. So what I am going to do is this. Okay, so I am going to define a new function. I just have to shift it a little bit, so to make the this variable is a problem. You see, it is from 0 to t, right? So here it is from t naught to t. I just have to shift the variable now to make it 0 to t, and then I can use the Gronwall, right? So what we do is this: you define u of t, right? U of t, capital U of t, to be v of t plus t naught. Okay, if you do that, you see u of 0 is nothing but v of t naught. So this is u of 0. Clear? Okay. So what do we have? Then that will imply that u of t, which is equals to v of t plus t naught. Okay, v of t plus t naught, and that will be bounded by v of t naught, okay, plus t naught to t plus t naught k times vs ds. Okay, u of t, you see u of t is v of t plus t naught, right? So I will just writing v of t plus t naught, and that is always dominated by, here you see it is, I will just change the variable here. So basically from t naught to t plus t naught, this will change. Okay, so I can write it like this. This is what I am doing here. I hope this is clear. See, this holds for all t, this holds for all t, so this holds for t equals to t plus t naught also, right? So I will just, I'm just doing that part here, and the variable is from t naught to t plus t naught. That is what. Okay, so that is there. Now this is nothing but v of t naught plus 0 to t, okay, k u of tau d tau. Okay, I will just change v, this v to u, and then the this integral becomes 0 to t, right? Yeah, therefore you see, therefore one can say, from here one can say that v of t plus t naught okay, is less than equal v of t naught times exponential kt, right? That's what we can say. That will imply that what is v of t? Then it will imply that v of t is nothing but, it is dominated by v of t naught times exponential k t minus t naught. Here, okay, and this is what the conclusion is. This is what the conclusion is. Okay, so we have the, the continuous dependence on initial data. Okay, so what do we have is, essentially you can say that if you have a system which is, let's say, Lipschitz continuous in the whole whatever the domain is. Okay, so if you have a system such that this vector field is Lipschitz continuous in wherever it is defined, let's say from omega, it is defined on omega, it is Lipschitz constant in omega. Do you think it is C1? Okay, let's say if it is also C1, so basically Lipschitz constant, Lipschitz continuous, along with that it is C1, right? And then you can actually say that the problem is well posed. Clear? Okay. So why Lipschitz continuous and C1? Does Lipschitz continuity imply C1? Of course not, because fx equals to mod x. As you know, this is Lipschitz continuous in R, but it's not going to be C1 in R. Okay. So with this, I am going to end this video.